Okay, hi everyone. I hope this video finds you well. So today we are going to talk about the callable units, main function, the program stack, or what's called the call stack. So the duplicate code is a block of code that occurs more than once, either within a program or across different programs, and it's also called cloned code. So the duplicate code is generally considered undesirable. We don't want such code because we don't want to have repetitions in our code. So inappropriate code duplication may increase maintenance costs and may be a sign of a sloppy design. So if a code is repeated that performs an identical task, and if later you need to make a change, then all instances of that code must be updated. So finding and testing all code segments is insufficient. If an instance is missed, this can lead to a bug. So if each of these stormtroopers needed the same update, we would have to find, update, and test each one to verify that it is fixed. So we try to avoid copying code. This is what I wanted to say. So the ability to reuse code without duplication is built into most programming languages. This is the ability to create callable units, and this is our topic today. So callable units basically is a group of instructions that perform a specific task. Those instructions can be packaged as a unit. So this unit can be used in programs wherever that particular task should be performed. So different programming languages call them differently. So in some programming languages, they are called procedures. In the C++ we are learning, we call them functions. In languages like Java, they call them method. In languages like assembly languages, for example, or pseudocodes, usually they call them routines, subroutines, or procedures. So we're going to call them from now on functions because you're learning C++ programming language. So in C++, callable units are called functions, as I said. The main function that you use to create your Hello World program inside is an example of a callable unit. As you can see, this main is a callable unit. So advantages of callable units. One, they break large programs into smaller pieces. Two, they reduce duplicate code within a program, enabling reuse of code across multiple programs, dividing large programming tasks among various programmers or various stages of a project. They also help in hiding implementation details from the user of the function. And this is going to be introduced to you later next quarter. Also, they improve debugging. So most languages offer ways to obtain the stack trace, which includes the names of the involved functions. You're going to see that later this quarter. Disadvantages of callable units. Calling a function versus using inline code imposes some computational overhead in the calling mechanism, which usually we tolerate. So the subroutine or the function typically requires standard housekeeping code for entry of the function, exit of the function. So the entry and the exit, something like that. So there is 0 to many parameters to the function, and there is always a return value, even though it could be nothing. nothing is still considered return value because we return nothing, but we do something. We certainly do something inside of the function. So the callable unit may need information to do their job, and they can return an answer to the caller. So the main function. The main function is your starting point. So the main function is the starting point in every program you have. This is one very important keynote. So most modern programming languages are stack-based. This means it uses a stack to keep track of what callable unit is running. So it's like a stack of plates you can either add to the top, which we call push. We push information to the top, or remove from the top, which is called pop. So pushing information, pushing data to the top, and usually in this case, we are pushing functions to the stack, or what we call stack frames. We are pushing them to the top of the stack, or popping them off the top of the stack. So you can only access the top of the stack. So the stack is LIFO structure, or last in, first out. The last plate in, the first one out. The last stack frame in, the first stack frame out. The stack frames contain data about the function. So the program stack is used to, one, keep track of the current function that is executing, keep track of the current code within that function that is already executing, pass information from one callable unit to another, one function to another. There are two types of information it handles. Arguments, which is basically the information the function may need to do its job, and return values, which is the result of the job it was asked to do. So a stack frame holds the function information. Each stack frame corresponds to a call to a function which has not yet terminated with a return. When the function terminates, this is why we say which has not yet terminated, because when a function terminates, it's gonna be popped off of the stack. So we pop it off when it's done. So for example, if a function named drawLine is currently running, having been called by drawSquare, the top part of the call stack might be laid out like the picture on the right. Like we have the drawLine above drawSquare. And you can't forget about this chart and even this slide because it's not exactly happening this way, but this is a good illustration that you may understand what's going on in the stack. So the program stack or call stack, the bottom item in the stack is always the main function. Always the bottom item is the main function. Because remember, the main function is your starting point. If the main function calls a function, a stack frame of the new function is pushed onto the stack. The instructions for that function begin to run. The main method, the main function, waits for the called function to complete its job and give it the information it was designed to calculate, the return value, to return a value to the caller function. In some cases, it has no information to return, but it has side effects, like printing something. Printing something, you do not return anything to the caller function, but you show something on the console. So a simple stack would be like this. Always the bottom line is going to be the main function. And if you called function A, for example, then the stack pointer that was pointing to the top of the stack, which was pointing to the main, now points to A because you pushed A. If A called B, then the stack pointer points to the top of B function because you pushed B. When you're done with B function, then you pop it off. Same thing with A. Finish that, pop it off. Then when you pop the main off, then you terminate the whole program. Because the last thing that is executing is the main function, the last statements in the main function. So again, key things to remember. The main function is the starting point. When a function is called, it is pushed onto the stack. Functions get information to do their jobs from the caller. The caller is basically the function that is asking for the work to be done. And the information it provides to the called function are arguments. Functions return information when they are done, which we call return value. Function stack frame is popped off of the stack when it is done. There is only one program stack, so there is a stack per program. Every program you have is only having one stack. Do we have many stacks? Yes, if we have many programs. But for one program, you have one stack. So side note, this is a very simplified view of how the stack works. As you learn more, you will add to your idea of how it is working. So understanding the basics of the program stack will help you understand many other later concepts. So don't worry if it's a little bit fuzzy right now. It won't stop you from programming, but it's good to understand these kind of things. Again, remember these things. Okay, let's talk about these stack frames a little bit in details, also called activation records or activation frames. So these are machine dependent and data structures containing subroutine state information or function state information. Each stack frame corresponds to a call to a function which has not yet terminated with a return. They usually contain the arguments, the parameters values passed to the routine or to the function, if there is any, because remember, it could be 0 to many. The return address back to the routine's caller, and space for the local variables of that function. For now, you can disregard this level of details. Just realize that these are what we are pushing onto the call stack and popping off the call stack. We are going to simplify it today, but you should understand that these are the things usually included in the stack frame we are going to represent today. So every function call has a corresponding stack frame that keeps track of the information related to it. So what is always the first step? Always. So note 1, instruction list is the example. In the example, such as like instruction at 50, instruction at 90, and so on, represent any line of code that does not call a method. So the number 50 in here is a hypothetical location that is, or that would be fetched from. So basically that is something like cout your name. Note 2, the program counter. This program counter. So this program counter changes through time. So there is only one address in the program counter at a time, and the list is just to show you, this list is just to show you that is actually changing value. So this is not an array or something like that. No, you can think of it as the change we do to the program counter. But the last item is going to be the item we are executing, and I'm going to show you how. So if we have this example, we have the main function, and it has 3 instructions. Instruction at 90, which is regular instruction, a function call instruction at 91, and another instruction at 92. We have function B and function A with their instructions as well. So the main method is always your starting point, always. So the program counter set to 90 at first, 90. Then the instruction at 90 is fetched, executed, then the program counter is set to 91, right? Remember, whenever we fetch an instruction, the program counter start storing the next instruction. So as we store 90, as we fetch the instruction at 90, then 91 is placed at the program counter. And we push the main function because we start always from the main function. So what happens next after we have 90 and 91? 90 is executing this one. 91, we finish 90 and then we fetch 91. 91 calls A. So we move to A and we start from the first instruction. So the next program counter is going to point at 50. Is going to point at 50. And remember, whenever we move to a method, we put that method or we push that method at the top of the stack. So what happens next? We execute 50 and we place, as we execute 50, we place 51 at the in the program counter. We finished executing 50 and now 51. What does 51 indicate? It says call B. So we move to B. We move to B. We don't continue with A yet. We move to B. So we move to B, then we are going to point at program counter stores 40. So here is 40. Is there any instructions left after we execute 40? No, we go back to the caller. Who called B? Who called B? And remember, whenever you call a new function, you put it at the top of the stack. Even if you called it before, that's okay. You put it again. You put it again. So A calls B, so we have A, then call B. If B, for example, called A again, so we put A here. If A calls B again, we put B here until we remove them. Even though that would be infinite loop, but anyway, just illustrating to you. Okay, so we are at 40, we finished 40, we go back, and since there is no instructions there, we pop off this one. So pop off A and go back to the instruction after the call. The call was at 51, so we go back from 40 to 52, from 40 to 52. Then we execute 52. Is there any more instructions? No. Okay, then go back to your caller, to the main function. The main function, the next line is at 92, so we push 92 and we pop off A. So now, is there any instructions left in the main method? No. So we pop off the main, which is basically represented in here, that thing you don't see. So that's it. That's it. We are done. This is the trace of our stack, and this is the trace of, or the changes we have done on the programming counter. So that's it. Just reminding you of a few things before we move on to the example sheet. So the main function is the starting point in every program. It's designed to be the designated entry point to a program that is executed in a hosted environment. which is basically your operating system. The program stack is used to keep track of the current function that is executing, keep track of the current code within that function that is executing, pass information from one callable unit or one function to another. There are two types of information it handles: arguments, input to the function. The function may need this information to do its job. The return value, the result of the information. It could be nothing, but then if it's nothing, then the function has some kind of side effect, printing something. Local variables are the variables we are going to talk about in the next lecture, and it's basically storage locations we use to store our data. So programming stack example, this one, the one we just done, this is the answer to it. Now we're going to move from the slides to the PDF slide to the PDF example sheet, and there will be exercise sheet that you should complete. Now whether you complete on a paper then take photos, or you do simple things like these in the Word document and you do that, but there will be like 8 exercises you do. But here's 2 questions to think about. Based on what you know so far, how many items can be placed on the stack at one time? So how many items can be on the stack at one time? And here's another question. How many functions can a function be waiting for to complete some task for it? Now the answer to those questions is basically, for the first one, you can have as many items as you can and the memory can handle. For the other one, for this one, the function can be waiting for so many functions, depending on your program and how you designed it. And again, as long as the memory, the RAM, can handle it, can handle this amount of functions. Okay, now we're done with the slides, and let's go to the call stack examples. So here's the first one. We have the main function. And we have function B and function A. So we start always with the main function. Instruction at 9. So we start at 9. As we complete instruction at 9, we put 11, the next instruction number, in the program counter. So 11 calls A, so we move to A. Now remember, when we started the main function, we pushed the main stack frame. Then it's still pushed, but then we moved from the main to A, so we push A. Execute the things in A, only one instruction, so 40. We finish 40, then we go back to 12. So 12 should be in the main function, in the program counter. We execute 12, and as we executing 12, and remember, since we left A, if we lift it to the caller function, which is what we have done, then we pop it off the stack. So we end up with only the main function. Then main calls at 13 calls B. So 13, what is the next instruction to be put on the program counter? Is the first instruction in B, so 30. After 13, we have 30. As we execute 30, and don't forget to push the B stack frame, B calls A. So we push A, but before that we have to push to change the counter to 40. So 40, then 40 completes. After we push this one, completes, remove it, and then after you remove it, you go back to the caller. The caller was B. So here it is, main and B only. we do the 32 we have in here. Then 32, after that, we go back to the color of B because we don't have anything left in B. So that was 14. We executed 14 with the main, and this blank means that we are done with main and we popped it off. So I'm gonna do this one very fast. 10 in the program counter. 11, as we are executing this one, we have 11. 11 means call A. We go to A, and as you can see, the changes in the stack frame. We push A at the top of main. We do 40, 41, 40, 41, and then we go back because we don't have anything left. We go back to the caller function. The caller function was A, so we do 12 and 13. 40, 41, 42 in A, 3, 31 in B, and 10, 11, 12 in main function. Let's start. So we first push main, then main calls B, and again, if something is not called like B in here, we don't push it on the stack, only what's pushed, and the controller here is the main function. Same thing in here. Main function, 10. We have 10 in here. Then we push 11. 11. What 11 means? Means call B. Go to B. 30, 31, 30, 31, and we pushed B. Then we pop it off because there is nothing left. And then we do the 12. 30, 31, and then we do the 12. And so on for all these things. Now I left this one for you. This one for you on Canvas. And this is the exercise sheet. This is the exercise sheet. So the exercise sheet has set of exercises. It has like 8 of them. So you do them. You show me the change in the stack here and change in the program counter. The change in the program counter for each of these. Okay. That's it for today. You can do this sheet by having this printing them or having them, or just show me the answers to the program counter, the changes in the program counter, and the stack for each example, or sorry, for each exercise, and take photos, scan them, do them in the Word in a Word document or any other thing of your choice. Okay, that's it for today. Thank you. See you in the next one.